All right, so today we're going to do the linear motion video part 2. Well, we've talked about displacement equations. Now we're going to look at equations that don't require us knowing the final velocity at the beginning. So we had the d equals 1/2 vi plus vf times t, and we had the vf equals vi plus at. Well, what if we solved for the VF, and then we put the VF into the first equation, so we no longer had a VF? Well, then we get something that looks like this. D equals VIT plus 1/2 AT squared. And that is our go-to equation for displacement. If the beginning velocity happens to be 0, then this term can drop out. And that happens quite a bit. Or if we're just making a quick calculation, we can say, oh, well, if VI is 0, then we'll just do 1/2 AT squared. So sometimes you'll see us just skip this part, but it's important. And if you have an initial velocity, it has to be in there for the problem to work out correctly. Okay, some practice problems. Here we go. How are we going to solve these? All right, for this problem, we've got a ball rolling up a hill, and it accelerates at a negative 5.6 meters per second squared. A lot of times people will say, well, isn't that deceleration? Well, in physics, we'll just call it acceleration, whether it's negative or positive. The sign's going to tell us what it's doing, whether it's slowing down or whatnot. In this case, it would be slowing down for 6.3 seconds. If it's rolling at 50 meters per second initially, how far is it rolled? Well, they didn't give us a final time, but let's write down, a final velocity. Let's write down what they did give us. We've got A is equal to negative 5.6 meters per second squared. We've got our initial speed was 50 meters per second. Okay, they're looking for a distance, d equals question mark. They gave us a time. Time equals 6.3 seconds. All right, so the equation we're going to want to use here, since we don't have VF and we're looking for D, is VOT plus 1/2 AT squared. That's a go-to distance formula that we'll use a lot. All right, so we don't need to rearrange it because we're looking for D, so let's just plug in some numbers here. We got 50 meters per second times 6.3 seconds, and we're going to add to that half of our acceleration, in this case negative 5.6 meters per second squared, and our time squared, 6.3 seconds squared. Okay, if we look at the units here, this squaring of these seconds is going to cancel out with those seconds. So this term here is just going to be meters. This term as well is just going to be meters, which is a way that we measure distance. So we're on the right track, it looks like. Okay, so 50 times 6.3, 315 meters. And then negative here, this whole term is going to be negative. So when we multiply those together, we get negative 222.26 meters. I know that's too many sig figs. Just going to roll with it. So I'm going to end up with 92.7, or about 93 meters. All right, another example. If a car decelerates, and I just said that, a lot of times in physics they'll just say accelerates, but in this case they're saying decelerates. So let's see, if a car decelerates at a rate of negative 6.4, let's see, let's fix that. Erase that. Grab the pencil again. negative 4.64 meters per second squared. Our distance, 162 meters. Our time, 3 seconds. How fast was it going initially? Well, our formula, just like the previous problem, d equals VOT plus 1/2 AT squared. In this case, we're trying to solve for VO, and it looks like we have everything we need. So what I'm going to do here is I'm going to say d minus 1/2 AT squared equals VOT. Then I'm going to divide both sides by t, so I'm going to get d minus 1/2 AT squared divided by t equals VO. That's a t. Alright, so what do we got? Our distance was 162 minus, and since our acceleration is going to be negative as well, a minus is going to be a plus. So plus 20.88 divided by 3 seconds. Okay, if we look at our units again, we've got meters per second there. We got seconds squared there, so that's just going to be a distance. That's going to be a distance. And we're taking a distance on the top and dividing it by a time in the bottom. Distance divided by time is velocity. So we're on the right track there. That's an S. Okay, and that's going to equal 60.96. And don't forget to label meters per second. And that's how you do that. All right, for this problem, we've got a ball rolling up a hill, and it accelerates at a negative 5.6 meters per second squared. Okay, well, that was a little bit too much there. Sorry about that. So what if we needed an equation that we didn't need, or we didn't have t? Well, we have this equation, and we can solve that for the t. And then we have this equation. What if we put this in here where the t goes, and we do some algebra magic to it? We get this useful formula. 2AD equals VF squared minus VI squared. A lot of times you'll see it written like this. VF squared equals VI squared plus 2AD. So here's an example using that. And let's. Alright, in this problem we have a bowling ball and it's being thrown, that sounds dangerous, at a speed of 6.8 meters per second. So let's see, I'm going to call that my initial velocity, 6.8 meters per second. By the time it hits the pins 63 meters away, well, that's a distance, so 63 meters. It's going 5.2 meters per second. Well, that's another velocity, so I'll call that my final velocity, 5.2 meters per second. What's the acceleration? All right, they didn't give us a time, but they're looking for an acceleration. Well, if they didn't give us a time, and we're talking about velocities and accelerations, usually the equation we go to is this one, plus 2AD. Okay, we're going to have to solve that for the A, so I'll use my mad algebra skills here. And I got to divide that by 2D, and that will equal A. Okay, time to plug in some numbers. VF squared would be 5.2 meters per second squared. Now the squared is for the 5.2 meters per second, not just the seconds. And we're going to subtract 6.8 meters per second, and that whole term is squared. Okay, and then we're going to divide by, there should be an equal sign here. We're going to divide by 2 times the distance, 63 meters. All right, let's do our unit analysis on this. Up on the top, we're going to have meters squared over seconds squared. And on the bottom, we're going to just have meters. So what we're going to end up with is units of meters per second squared, which is what we want. So feeling good about that. All right, 5.2 squared is 2704 minus 6.8 squared is negative 19.2 divided by 2 and divided by 63, and we get our answer is A equals a negative 0.15 meters per second squared. Okay, well, we've got an acceleration term here, units, so that's good, but sometimes people think, uh-oh, that sounds weird, that sounds wrong, how did I get a negative? Well, that would indicate that the ball is slowing down during that time period, and it started out at a higher speed and it ended up at a lower speed, so that's consistent. And it's not really pulling like 12 G's doing it or anything, so it's not that big of a change in velocities, so that does make sense. So I do feel good about that. Okay, here are our big 4 equations that we've been working with, and we've showed you how to develop them across the 2 sections of video here. But these are your big 4. These are your go-to. Any kind of motion that we're trying to describe, these equations will do it for us. All right, now when we factor in gravity and we're working problems, there's some things that even if they don't directly say it in the problem. Probably you're on Earth, right? Gravity's going to cause acceleration. And on Earth, all objects have the same acceleration due to gravity. On Mars, all objects have the same different acceleration due to gravity. So differences in falling speed and acceleration are due to air resistance, not differences in gravity. So heavy things don't fall faster than light things in our calculations here. We can add in that air resistance later on, but we're just going to assume for all of these problems that there's no air resistance. And a lot of times they'll say that in the problem. For Earth, G, which is our symbol for acceleration due to gravity, is negative 9.8 meters per second squared. Okay, so when we're analyzing a falling object, we're going to consider the final velocity before the object hits the ground, not after it hits the ground. So a lot of times students will make the mistake of going, well, if this object hits the ground, it's going to be going 0, right, Perry? And I'll be like, yeah, after it hits, it will be, but we're looking at the instant before it hits. All right, so problem-solving steps. Again, there's a video on this, what I want you to show me when you're doing this. I'm going to give you a little bit more independence in the rest of the video. I'm not going to show you how to work out every single thing, but I will give you some hints and I'll give you some answers and we'll see how you do. So identify what the givens are in the problem, write them down, determine what is being asked for, write it down with a question mark, select an equation that uses variables known and unknown that you're dealing with. Sometimes you might pick the wrong equation, might go down a blind alley, realize halfway through that's not what you want to do. That's okay, that's normal, that's physics. Come back, figure it out, solve the selected equation for the unknown, fill in the known values, and write your answer with the units. So hidden variables are things that are implied in the problem that might not be stated. If an object is falling through space, we can assume it's on Earth and it's falling at negative 9.8 meters per second squared. Why the negative sign? Well, you can decide whether going down is positive or negative as long as you keep everything consistent. That would mean that going up, if you said down was positive, up would have to be negative. Most of the time, our convention says if we're going down, it's negative, but that's fine. It's up to you, just as long as you keep it consistent. Starting from rest, when they say this object is starting from rest, our initial velocity is 0. When they say we come to a stop or something like that, our final velocity would be 0. And a change in directions indicate that at some point your velocity was 0. So dropped objects have no initial velocity. We're just going to say that our VI is 0 unless they specifically state otherwise. So one of the things that we're looking at here with a ball thrown upward at a speed of 5 meters per second is what's going to happen is gravity is going to slow it down on the way up. And then it's going to stop and have a speed of 0 at the top of the arc. Then it's going to start falling back down due to gravity. All right, so one thing that we know is when it reaches the top of its path, its final velocity is 0. And how long does it take to get there? Okay, well, VI is 5 meters per second, VF is 0 meters per second. A, or we could write G, negative 9.8 meters per second. We're looking for D, we're looking for T. So for part 1, I would use this equation, solve it for T, and I ended up with 0.5 seconds. For part 2, I would use this equation, solve it for D, and I get 1.28 meters. A lot of times in physics, there's more than one way to solve a problem. Valid ways. You might have chose different equations to get to the same point. The answers should be the same as long as we're both using the same mathematics. These formulas can be interchanged. You can use what equation you feel is right for the situation. That being said, here we have a situation where we have a plane slowing down on a runway from 207 kilometers per hour to 35 kilometers per hour in 527 meters. Okay, question is, what is the acceleration and how long does it take? I'm going to give you some tips on this and I'll give you my answer. So why don't you pause the video right now, work the problem out, and then restart it, and I'll go over some tips. Okay, the first thing I notice here is that we've got kilometers per hour and we've got meters. So at the very least, we would need to change it to meters per hour. I'm guessing that it's not going to take the plane that long to decelerate, so I'm probably just want to change the kilometers per hour to meters per second. Check out the video on changing units. That's a really important skill. And so then I would change those units and I would get that the plane is decelerating at -3 meters per second, about that. And then once I got that answer, and I would probably use my VF squared equals VI squared plus 2AD equation to do that. For the second part, I would take that acceleration that I got and just plug it into VF equals VI plus AT, solve for T, and I get about 15.7 seconds. All right, the next problem here, we have an onion falling off a cliff. And the cliff is 84 meters high. How long does it take him to hit the ground? It's a boy onion. Look at that. That's crazy. All right. Well, I'm going to give you some hints and the answer. So why don't you pause the video now and restart it when you're ready to hear the hints and the answer. All right, in this problem, we've got the distance of 84 meters. I would just say that VI is 0 because we're dropping the onion. And when we end up solving the problem, I got 4.14 seconds. Okay, now here's a different one. We've got an onion being thrown upward It's going to go up initially at 9.5 meters per second, and then it's going to come back down. Well, how long does it take the onion to hit the ground now? Pause the video. I'm going to give some hints. I'm going to give what I got for the answer here. Okay, there's a couple of ways to do this. You can set this up using the d equals VOT plus 1/2 AT squared equation. Solve for t and then use the quadratic formula. You got to write the equation in the ax squared plus bx format and then put it in the quadratic formula. Or you could, and solve for t, or you could break it up into two parts. How long does it take to get to the top, which we know VF would be 0 at the top of the path. Okay, so you can calculate the time for that. You can calculate the distance, add the distance to the distance of the cliff, and say, well, if I went up there and dropped it from that height, how long would it take? Add that time to the other time. And what I ended up with was about 5.2 seconds for that onion to get to the ground. Okay, here we have a cow that's on the railroad tracks. Train engineer doesn't want to make a mess and lose that livestock if he can help it. So the train's going 40.7 meters per second. It's decelerating at a rate of negative 1.4 meters per second squared, and the cow is 500 meters away. Will he be able to stop in time to avoid hitting the cow? Okay, pause the video now and I'll give some hints. Try to work out the problem. Good luck. All right, most people, when they make a mistake on this, use the 500 as the distance. You don't want to do that. The 500 is how much you have to work with. You want to calculate the distance on your own, okay? Then compare it to the 500. If it's bigger than 500, the cow's in trouble. If it's less than 500, the engineer can stop in time, all right? So that is one thing that people do often. So I would use the VF squared equals VI squared plus 2AD, solve for D, and when I did that, I found out the cow's in serious jeopardy. I got 591 meters for this big old train to stop. Okay, distance or position versus time graphs. When you do a graph like that, this slope of this line is your velocity because this is distance divided by time. The steeper the slope, the faster, the higher the velocity. If you see this sort of thing, if you see a line with no slope, that means the object has stopped moving. You can see it's at 25, at 5 seconds, at 6 seconds, at 7 seconds. So it's just sitting there. It's stopped moving. Now this becomes really important when you're looking at calculus because calculus is all about graphs and calculating the area under the curve or calculating the tangent to a line. So that's why I'm mentioning it. It's very important. It's also important to be able to read a graph. Now if we have velocity versus time, what we're looking at is the slope of this line is the change, your acceleration, right? The change in velocity over time. And so what we've got here is, you've got one slope, and then you've got a different slope, and then you've got something else happening right here, and then you've got a negative acceleration coming down. Okay, so this would be like a ball being dropped. It's accelerating faster, it's accelerating faster, and then boom, it hits the ground. Okay, and then it changes. Now also when you cross the y-axis here, the x-axis, sorry, the x-axis, that indicates a change in direction. So this part of the acceleration is in the opposite direction. Velocity is determined by reading the graph. Acceleration is determined by reading the slope of the graph. Displacements found in the area between the curve and the x-axis. The areas above the x-axis are considered positive, and those under are considered negative. So you could, break this into triangles or whatever, or you could just use calculus. Okay, so some questions about the graph. Should be able to read a graph and be able to figure out simple questions like this. That's the end of our presentation today. Enjoy!